typed the whole command line and then did not press the return key. That happened more than once already. Okay, so the final exam time of this class is the same as the scheduled time, in the final exam schedule. And I think I put it into the syllabus, but I need to double check to make sure that is in fact the correct time. The final exam schedule is here. This is a Tuesday, Thursday class. We are starting at 10:30. So that means our final exam time is in fact May 14th from 10:15 to 12:15. Okay, so we have a 2-hour final exam basically next Thursday. Next Tuesday, I will give you a practice exam, so you guys can kind of see what kind of exam questions will be coming your way on Thursday. Okay. Are there any questions about the final exam? It's going to be open book, open notes, just like with your first 2 exams. Yep.
Do you expect it'll actually take the whole 2 hours?
That is a really subjective question. I have no idea whether the answer. Okay, I'll put it this way: the answer is a function of you. Yep.
Is the final like the same difficulty as the other midterms?
That again is a function that involves you. You are a part of the domain of that function. It's hard to tell. I cannot tell. I do not intend it to be difficult to the point where you will not have enough time to finish it. I will put it this way: you do have to understand the material that we have talked about in this class. That much is for sure. Okay. Alrighty, but it is open book, open notes. I will bring my cheap calculators along with me. I don't think it's going to be really helpful, but I will bring those along anyway. Okay. Alrighty. So now that we have the final exam time out of the way, we can now go back to this class, and we are. This is the wrong class. We have a homework assignment, so I'll give you a view of the homework assignment first if you have not seen it yet. And then we'll go ahead and do it once in class so that you know what I'll be expecting from your answers. All right, so the homework assignment is simply called Dijkstra's algorithm. The other algorithms are a little bit harder to trace, but Dijkstra's algorithm is relatively easy to trace. And I will show you exactly how I want you to do it. There's a spreadsheet format to help you do that. So we'll click on the homework assignment and take a look at what the homework assignment is asking first. All right, so there we go. So the homework assignment is to ask you to use Dijkstra's algorithm to find the distance from an origin vertex to each of the other vertices. Okay, so you basically have to calculate what is the shortest path, what is the shortest distance from the origin vertex, which is vertex A, to all of the other vertices. And I'm going to give you the definition of the graph and also the cost of the edges as follows. So the graph is a typical definition. It's a 2-tuple. One is the set of all the vertices, and the other one is the set of all of the edges. The vertices are simple. Okay, we are just defining A, B, C, D, E, F, G, H, I as the vertices. And then the edges are 2 tuples, which means this is it a directed graph or is it an undirected graph? When I use a tuple or 2 tuple to represent one edge, it's a directed graph, otherwise known as a digraph, right? Okay, so it is a digraph, it is directed, and then we have a function to map all of these edges to a real number. That is the cost function of each edge. So the cost of edge AB, in other words, when you go from vertex A to vertex B, is going to cost you 2 units of whatever, okay? So with all of these definitions, I want you to basically show me how much it will cost. What is the least cost from the origin, which is A, to any other vertex in this particular graph? So that's what you need to do. Yep.
If we decide we want to use pen and paper to do this instead, which I can see is long but viable, can we scan it in and turn it in?
Well, I just created one of those things last night, and it was a little bit challenging. Okay, so you do have to follow the same format that I'm showing you today. Okay, So even if you do it on a piece of paper with pencil and paper, I still want you to use a table format the way I'm going to show you today. So you might find it actually easier to do it using an actual spreadsheet. Okay? It's up to you. But I will look for the same thing whether you use paper and pencil, as opposed to okay, here's my Google document, and it is based on the actual document that we are going to work on today. All right. Okay. So at the end of this page is there's one graph here. Well, I can do this later, but there's a spreadsheet here that you guys can view already. It is a hyperlink to a Google document, and this is the spreadsheet. It is not your homework assignment, so this is definitely not the exact same graph as the homework assignment, but it is similar. It is a smaller one, but it is very similar to what you have to do. Once again, the graph G is defined to be BE. Okay, B is the set of all the vertices. A, B, C, D, E in this case. There are only 5 vertices in this particular case. And the edge, E, is the set of all the edges. And in this case, we have, 8 edges, okay? And then the cost of each edge, function F, is also defined here. So the cost to go from vertex A to vertex B is 5 units of something. I maintain a maximum here because there's no way to represent infinity in a spreadsheet, so I will have to use this one to quote-unquote represent infinity, and there's a reason why I have to do it, because the Dijkstra's algorithm requires the representation of quote-unquote the infinity value. This is a hyperlink to the actual algorithm itself. In other words, this spreadsheet is somewhat self-contained. It shows you the algorithm, it shows you what the vertices are, the edges, the cost of each edge, and then the other sheet, which is worksheet here. This one has the format to help you do it. Okay, so what I'll do today is I'm going to do it myself this time, but you will have to set up a spreadsheet about the same way to show me the steps to solve the problem. Do we have any questions at this point? All right, well, without any further questions, what I'll do is I'm going to follow this link here and show you the algorithm itself. It is from Wikipedia, so if you want to make sure that you are referring to this particular algorithm, you might want to bookmark this revision of this wiki page, because as somebody pointed out the other day, someone can go in and quote-unquote poison Wikipedia and change the algorithm to something else. So if you want to make sure that you're always referring to the right algorithm, you can always point to the one that is effective today at this time. Does everybody know how to do that? Go through the revision history of Wikipedia and just use a particular version. You don't know how to do it? Okay, let's go ahead and do that. So we'll go back to actually work on the algorithm later on. And view history. Okay, so I'm going to do a right click here just so that we don't lose the original page. So here you can go through a list of all the changes, and you can limit the time from year and earlier, from month and so on and so forth. And you can basically now go through the history, browse the history, and you can see each time someone changes the document. The latest change was from yesterday, and you can also see what the changes are. Okay, so you can basically look at the div here. You can do the undo. I would not do that, because when you say undo, you're undoing the actual page on Wikipedia. So if you find out, okay, I'm doing this homework assignment and tech is using the algorithm as of, the 5th of May, then you want to kind of lock on to this particular version. And the way to lock on to this particular version is simply to click on the thing. If you just click on this link here, that will show you that particular version. It is the current version at this point. Now, on the other hand, for whatever reason, for some of your other classes, you find out that, okay, the current version of the document is inaccurate, but one of the earlier version is actually more accurate. What you can do is you can go back to a certain time. Okay, so you can scroll down back, to a certain time, right click, just click on it, and this way you can see that it is now the older version of this page. It is prior to all the changes after this particular date. So this is really helpful, especially when you do research and you want to find out whether some page can be trusted. You can actually go through it and find out, okay, who has made what changes to this particular web page. Okay. Are there any questions about this particular part, which is not specific to this class? No questions? Do you guys read Wikipedia for whatever purpose? Okay. Sometimes, okay. Okay, how many people spend more time on Wikipedia than Facebook or some other social media website? Okay, that's good. If you spend more time on Facebook than Wikipedia, well, I'll just put it this way, you're more social than I am. Or the other way to say is I'm more wiki than you are. All right. So now that we know how to locate and log on to a particular version of a document, we'll just use the current version of the document, which is here. And let me close this page. We'll just go to that link again. Because the link does not link directly to the top of the document, it links directly to the algorithm for your convenience. So this is the algorithm. There's really nothing really tricky about this. If you know how to read pseudocode, that's basically the only requirement is you have to know how to read your pseudocode. When you see something like this, it really is just like updating an array. Okay? Instead of using a single equal symbol to mean assignment, it's using a left arrow to mean assignment, which is a fairly typical thing for pseudocode representation. The only reason why we use a single equal symbol for assignment operator in C and C++ is because it's easy to type. Okay, it really does not make sense, but to programmers it seems to make sense. Is that okay so far? Does everybody understand why I said a single equal symbol to represent assignment operation does not make sense? Just ask your math professor, okay? For that one, you just ask your math professor. Does it make sense that x equals to x plus 1? Your math professor would just laugh at it and go like, no, it does not make any sense. But yet, to programmers, it makes sense. And then to make up for it, to even make the problem worse, when you need to check whether two things are the same or not, like whether x has the same value as y, what do you do in C and C++?
Double equal.
Double equal. What if you miss one of those double equals? Then you're actually assigning. Is that okay? Is it syntactically okay?
Yeah.
As long as the left-hand side is actually something that can be updated, it's okay. It's not a problem. But your program is not going to work the way you intended, in a very, very bad way. Because instead of checking whether something is the same as something else, you're updating it to be the other something else. And then you use the something else value as the Boolean expression to be true or false. So that is like bad. That's why C and C++ really should not have been a beginner's programming language. All right, well, enough about that. So what we'll do is we'll take a quick look at this algorithm, which is self-contained, and we want to figure out, okay, how do we apply it to the graph that we are trying to solve today? All right, so we'll just kind of follow the code here. The first thing we do is we initialize the variable, or initialize one of the elements in the array dist. Okay, dist is representing the distance to a particular vertex. In this case, source is the root of the entire thing, which means it is your origin. This is where you start. In both the homework assignment and the demonstration that I'm doing today, node A or vertex A is the source, it is the origin of the entire thing. Okay, so given that, what we'll do is we'll go ahead and update our document accordingly. And the worksheet is on the other side. You might need to open up multiple terminals to do this, simply because that, okay, I'll open it again. So this way I have two tabs. One, I will fix one tab on the definitions. I'll fix the other tab on the worksheet itself. So this way I can kind of go back and forth. Well, let me see if I can pull this out so I can do it side by side. I think it might be better if I can just do it side by side. I think I can do this. Yep. Okay. So actually, I need to pull this one out. Window. Resize this one. Okay, there we go. Okay. It's difficult. It's difficult for me, but it should not be as difficult for you, because when you do this on a large terminal with a small, font, you can open up many terminals at the same time and look at the same document from different views. But it's a little bit harder for me because I have to use the projector, which has a lower resolution to begin with, and I cannot shrink the font, to the point where you cannot. See, it's already complaining about my terminal is too small. I can fix that later, so it's not a big issue. All right. So getting back to the algorithm, we're on line 2 of the algorithm right now. We want to set the destination of the source to 0 because that is by definition 0. What is the distance of the source, which is the origin, from itself?
0.
0. Okay, doesn't cost anything to go to where you are already. So when you look at the spreadsheet, this is our origin here, and when you look at the worksheet here, you have to do the initialization. So the initialization is in column D, and then what you want to do is to update this one to a 0. Okay. Are there any questions about this part? Okay. And when you look through this code from line 3 all the way to line 9 is the initialization loop. This loop doesn't really do any real computation. What it does is to initialize all of the other elements. There are 2 arrays that you have to initialize. One is dist, which is representing the distance from the origin to that particular vertex, and the other one is pref, which is previous. Okay, it is remembering, what is the previous vertex of a particular one. So they are all undefined. In terms of pref, they're all undefined because we have not figured out the shortest path just yet. And then as far as distance is concerned, it is all infinity. This is why I have to mention infinity, which cannot be represented in the spreadsheet. Okay, but the summation of all the costs of all the edges is more than enough because you cannot find a path that is more costly than the addition or summation of all of the edges. Okay, so to do this part, okay, so let's go ahead and take a look at each line. On line 3, it says for each vertex v in graph, and you can see this is using a pseudo Python syntax because Python likes to use a colon at the end of something, but then Python does not use and for. Okay, it simply uses indentation to mean the nesting level. But I'm hoping that you guys will not find any problem understanding this syntax. So what this is it's basically using it's selecting each vertex in graph. But in our representation, the graph has 2 sets. One is uppercase V, which is the set of all the vertices. So in our case, it is actually for each vertex V, for each element V, lowercase, in uppercase V, do the following. So we'll have to do this, but we only do it as long as V is not the source, which in our case is vertex A. So back to the spreadsheet, what we need to do is to say, besides other than A, we'll go change all of the other ones. Now in queue is basically just checking whether something is in the priority queue itself. So A is not in the priority queue to begin with. And we'll start with a B. B does not equal A. The distance is going to be quote unquote infinity, but since we cannot actually use infinity, there's one way to refer to it. And let me see if I can do this. I think I can do it like this. There we go. There's the enter key. There we go. So it does work the same way as in Excel. You can do an equal symbol to mean that this is a formula, and then you can click on the other sheet and click on the cell where you want to refer to. Okay? Once you have one, there's a quick way to copy and paste this one. If you just copy and paste this right now, it's not going to work. The reason why it's not going to work is because the row number is going to shift, because when you copy and paste, and this is not an absolute reference to a row number, the row number will quote unquote float to where you paste the cell to. Okay, I'll do it once to demonstrate that concept. So I'm just copying here, and it will say, oh, okay, the distance of C or the origin to C should be the same, so I just paste it. But you can see that after I paste it, there's nothing here. Well, I'm not sure how easy it is to see the actual formula.
Yeah, C18, no problem.
This is C18, and then the other one, the one that is correct, is C15. And you can see the row number is changing, and that has to do with a particular way to refer to cells in the spreadsheet, application. Okay, so you don't want the row number to keep changing, and you can put a $ as an absolute reference, so that way you can copy and paste it as many times as you want, and it won't shift on you. So I'll just go ahead and demonstrate the idea here. So instead of just using C15, you can specify $15. Okay, and then press the Enter key. It does not seem to do anything differently on this particular cell. But now if I do a Control C and then go to other places to do Control V, it's all going to work. Okay, because when I paste it, the $ says do not change the row number depending on where I paste it. Without the $, it is in quote unquote relative term, and it does change it will change both the row and the column number, but since they're all in the same column, and that's why we don't see the column number getting changed. Are we doing okay so far with working with a spreadsheet?
So why do you have initials set for 43? Why do you have the initial set for 43 for distance previous?
Because it is the sum of the cost of all edges. The shortest path cannot have a cost that is more than this. It can be the same in the worst case, but it cannot be any more than this. Does that make any sense?
Is it for using for the pseudocode? Is it being set? How is it being defined in the pseudocode? Is that number being?
You mean the 43 itself, or why am I using 43?
Is the 43 is that type of thing defined in the pseudocode?
No, it is not defined. This is actually taking the place of infinity in the pseudocode.
Okay.
So when you refer to the pseudocode, and this is the pseudocode, see in the pseudocode I have to initialize the destination of each vertex to infinity. But since a spreadsheet does not really have a way to represent infinity, I have to pick a large number, a number that is larger than the actual distance to any particular vertex. And I just pick the sum of all of the vertices. Yep.
So wait, why is it at infinity? I'm not sure.
Because it is not known yet. The algorithm is going to compare the current distance to a potential new distance based on how you expand from the origin.
So
when
it
you
starts
find
at the max?
it started as a max, and when you find a shorter way to get to that particular destination, then you update it and say, oh, hold on, by the way, I found a better way to get here. And then you also have to update ref to indicate this is the other way to get here. It is a shorter path. All right, so are there any questions about this line in the pseudocode line 5 and why I use 43, which is the sum of all the cost of all the edges, to in place of infinity? You can type in like a really large number if you want to, like 10 to the power of 60 or something like that. But I'm just using the smallest number that will still make sense. Is that okay so far? Okay. All right. So we have to also define the previous to undefined for every single vertex other than the origin itself. So in the worksheet, you just have to say the previous is undefined. And this one, since I just typed it, you can just copy and paste it, and that would still be okay. All right. Are there any questions about the spreadsheet? In fact, let me see if I can, it's already in the compact mode. I cannot make it any smaller. I suppose I can turn off some of the bars. I can do this. Okay, well, at least it will show the entire thing here. Okay. And then the last operation is to add B to the queue. This is called a priority queue. A priority queue is basically a sorted queue where the items in the queue is sorted by a particular value. In this case, we're using distance to sort it, but since all of the vertices have infinity, they are all at a quote-unquote same priority level. In the spreadsheet, there's no way to actually represent it. The only thing we can say is they are in the set, in the priority queue or not. So I'm just going to put a 1 here to indicate that these 4, oops, I did 1 too many. This one should not be in the queue, and it should not even have a previous value. There we go. Okay. So the reason why, when I change one cell, the other one gets updated is because of this. It's because this one is actually an equation. It is taking the minimum of pretty much that entire row. So that's why, when I type a value in the row, this one gets updated automatically. You do not have to use the equations, okay? If you do not feel like using equations in the spreadsheet, you can just, manually update everything. Are there any questions about column D before we move on to something else, before we move on to the actual algorithm? No questions? It's all good so far? Okay. So let's move on in the algorithm. Maybe it makes more sense if I just put it this way. I think I can do it. There we go. Well, close enough. There we go. All right. So this way we can actually see the spreadsheet and the algorithm at the same time. So we're now moving on to the while statement. The while statement is saying, while Q is not empty. In other words, as long as we still have elements in Q, which is the priority queue, do the following. Is that okay so far? Do we have anything that is in Q at this point?
Yes.
We have a bunch of stuff that is in Q at this point. So what we need to do is to execute the first statement of the while loop, which is to pick an element out of Q that has the least cost, okay, the least distance from the origin. When you look at the distances of all of these vertices, which one has the least distance?
They're all the same.
They're all the same because they're all basically quote-unquote infinity at this point. So you can just randomly pick one if you want to. So I'm going to randomly pick one. Does not seem to make any sense. Actually, that is not true. That is not true. It forgot to do one thing. Well, I forgot to do one thing. When you look at your Q.add with priority, is it in the conditional statement or is it out of the conditional statement? It's out of the conditional statement. So the question is, should the source vertex also be a part of the queue?
Yes.
Yes, and I undid that. Okay, so this was my mistake. The source should be a part of the queue as well.
So
Now we can pick one, right? We can pick one that has the least distance, because when you look at everything that is in the queue, we actually have all 5 vertices in the queue at this point. But when you look at the distance from the origin to each of the vertices, one definitely has a lower distance or a least cost compared to the rest. Go ahead.
Should the queue priority be 0 because the distance of the source from itself is 0? Or am I reading?
Correct. But the 0 and 1 is just indicating whether it is in the queue or not. So I'm not even ordering yet. The ordering is implied by the actual distance. So you have to look at the actual distance and say, oh, okay, this is, what is the actual distance? And in order to maintain the current, which is actually very useful later on, I can now use a equation here. I can use exactly the same equation to put it here. That won't work. Because undefined does not work here, but distance will work. Okay. The reason why I want to keep this one here is because later on, as I work on iteration 1, iteration 2, and so on, I need to keep track of what is the current value of each vertex. And it's not easy to keep track later on, so I want to do it this way. And the equation to do this is to take the minimum of that row. That's basically the entire thing. That's how I keep track of the current value, because they cannot go up, they can only go down. Alrighty. So now that we can pick, okay, again, which one are we picking out of the cube? This is the first iteration. We're picking A out of the cube, and so that will make vertex A variable. It will make variable U to store the value of vertex A. Is that okay? Because U is a variable, it is supposed to store a particular vertex. So in the table here, I have row 2 to explicitly represent which vertex is U. So you basically have to say here, okay, this time we are picking A as the vertex, as the value of U. Are there any questions about how I put a value here, or why I pick vertex A as variable U? Okay, if there are no questions, we move on to the next few lines of the algorithm. This is a loop inside a loop. It's basically saying for each neighbor V of U, so now you have to say, okay, where can I go from vertex A, where else can we go? Yep.
So that would look up the definitions, so we have to switch to the page.
Right, if you look at the definition page, that would be helpful. And this makes it kind of complicated when you have a small screen like what we are dealing with here. That's why I kind of opened up multiple, terminals of the same thing. So when you look at vertex A, it has 2 neighbors. One neighbor is vertex B, the other neighbor is vertex D, okay? So what we need to do is to follow this algorithm in the worksheet. So B and D are the neighbors. So now we have to evaluate, okay, in the first iteration of the for loop, we have to assume that V is the same as B, right? So now we have to compute the alt here. The alt is basically saying, okay, what is the alternative distance from the origin to vertex B? Now, how do we compute that? Do we know the distance from the origin to U? We do know that, right? So in this case, it is 0, right? Do we know the length, which is the cost going from vertex A to vertex B?
Definition page.
Yep, in the definitions page, we have the cost. So we just calculate the alt, okay, from A to B. So you have to put that cost over here, okay? It's going to be 0 plus whatever that thing is, and I think we just look it up here.
5.
It is a 5. Press the enter key, So this way I minimize chances of me making any actual arithmetic mistakes because I let the spreadsheet do all the calculations. Is that okay so far? Alrighty. And it's not supposed to update this one just yet. Okay, so all of these really should be just 43. They should not be changed just yet. Okay, so this is one. And now that I have alt, is alt less than the current distance, the current known distance to vertex B? Okay, what is the current known distance to vertex B from the origin?
43.
43, or basically it's infinity, right? Is 5 less than infinity?
Yes.
It is. So we go into the conditional statement and we update the distance. So now we go update the distance. So now this one is now updated to a 5. So the equation would actually work too, but it's not showing you the step-by-step process, okay? Because I want to show you the step-by-step process by following the actual algorithm. So now we are done with the updating of the distance. Now we have to update the previous. How should I update the prev open square bracket V to U? What is V, by the way? Which vertex is V? B. And which vertex is U? Is A, right? So we go to the previous of B. Okay, this is where the scrolling needs a little bit more. So this is all. These are all for B. So we have to update the previous of B to be A at this point. Is that okay? Yep.
I'm not understanding that if alt's less than this B, because isn't this B the distance from A to B?
It's from the origin. There's only one origin. It's from the origin to the vertex B in this case.
So it's not just 5?
All is 5, but this B is initially infinity. That's how we initialize it. So when you look at column D, which is the initialization, you can see that for vertex D, the initial cost or distance to it is infinity, because 43 is going to go out infinity. That, okay, all right. So getting back to here, it says here, we want to decrease the priority, but we're not going to do it because we just look at the queue. Every single time we want to remove something from queue, we are going to basically change it. But queue does not have, U is no longer in queue because I forgot to trace this line here. To trace this line, it means U, which is node A or vertex A here, is no longer a part of the queue. So I have to change this to a 0 because now I just removed vertex A from the queue. So it will not be considered again in the future. Okay. So we are done with one iteration. Now we are back to the for loop here, because there are two neighbors. We just dealt with one. Who is the other neighbor of vertex A? It's actually vertex D. If I remember correctly, it is vertex D. Let's double check. It's vertex D, which has a cost of 7. That's the cost of the edge. So that's the other thing we have to do, is to go to vertex D and do some updates. So we'll basically do this part here. So we'll compute the alt, but this time for vertex D. So D is, okay, what is U, by the way? Have we changed U yet at this point? Variable U is still vertex A. And what is the current distance to vertex A from the origin? It's 0 because A is the origin itself. What is the length or what is the cost going from vertex A to vertex D? We just looked it up.
7.
It's 7. 0 plus 7 is 7. So the alt for this particular vertex is 7. So now we indicate 7 over here. Okay. Now this is the initial condition. In other words, this is what we know as the distance to vertex D. This is the alt. Okay. This is basically saying, okay, I'm considering this new distance to this particular vertex. So now we move on to the conditional statement. Is alt, which is 7, less than the current known distance to vertex D, which is infinity? 7 is less than infinity, so the answer is yes, it is true. We go into the conditional statement, and then we update the distance to vertex D to 7. So this is now updated to 7. And we also want to update the previous node to the previous node vertex. I keep saying node because that's the term that I learned when I learned graph theory, but it's the same thing as a vertex. The previous vertex to vertex D should be vertex what? What is vertex U at this point?
A.
It's A, so we update it to A as well here. And then we change the priority, but that's not, we're not going to do that because we just look at this particular column and pick out whoever has the least distance, and that's how we will do it. All right, so we are now at the end of the second iteration of the for loop, as far as A being U is concerned. Are we done yet? Do we have any more neighbors coming out of vertex A?
No.
Nope. We only have two neighbors, and we just dealt with both neighbors. And that's why we're going to end the for loop, which is ending the while loop here. We go back to the beginning of the while loop. Is the queue empty at this point? The queue is not empty at this point because we still have B being in the queue, C is in the queue, D is in the queue, and E is also in the queue. We have 4 elements left in queue. And out of these 4 elements, which one has the shortest distance from the origin? vertex B. Okay, how do we know vertex B has the shortest distance at this point?
It's cost.
The dist, the value of dist is only 5. The other ones are 7, infinity, and infinity. Okay? So out of these 4 remaining elements, I'm going to pick B as my next one. So this is where you can use another trick with a spreadsheet, which is to use this bar here and kind of just move it over here so that you can scroll one side without changing the other side. So this way it's easier to keep track of what you're doing, and it's just easier to track what you're doing with this particular column and update the current values at the same time. Are we doing okay so far with this part, how to make use of the split screen feature of a spreadsheet? This will work as well if you use Excel or LibreOffice. Okay, it's a really useful feature when the size of your monitor is limited. Okay, so we're gonna pick who as variable U this time. Of all the remaining elements, which one has the least distance? B. Okay, vertex B has the least distance. So we have just completed this line here, and we have to extract. When we say extract, it means we are removing that particular element from Q. So I have to remember that Q is no longer here. So I put a 0 here. And since that value is taking the minimum of all of the entire row, the moment we take something out of the Q, it is reflected in the current column. Does everyone understand that part? No? Yes? Sort of? Okay. If I double click on this one, you can see that it is not a fixed value of 0. It is taking the minimum of all the values of all the cells of that particular row. And since it's initialized to 1, that's why the minimum was 1. It does not use text as a part of the calculation. But as soon as I put a 0 here, because 0 is less than 1, so the minimum is automatically updated to 0. So this is an easy way to keep track of the current value, so I don't have to go back and forth to update it manually. Okay. All right, so we are done with this particular step, extracting a particular element out of U. And now we are going back to this for loop here. We have to first find out who are the neighbors of this particular vertex, which is B. So we switch back to the definition page, and we can see that B also has 2 neighbors. C and E are the neighbors. And we'll go ahead and look at the cost as well. The cost of BC is 1. The cost of BE is 11. Okay, so just kind of remember that. So when we go back to this trace here, we can go ahead and do it. Okay, so for each neighbor V of U, do the following. This part is not necessarily you don't have to go with C and E in that particular order. You can change the order if you want to. In other words, you can change the order to E and C because the for loop does not clearly indicate which one has to be evaluated first. But I'm just going to go for C and E because that's the way the list goes. So the first one is I'm going to pick C as variable V because C is a neighbor of vertex B. What is the current known distance to vertex B? It's 5. What is the cost to go from vertex B to vertex C? It's only 1, and that will make the alt 6. Okay, very good. So we update the cost, the alt to be 6, and then we evaluate the conditional statement. Is 6 less than 5?
No.
The answer is no. Okay, 6 is less than 5 is false, which is basically saying we have not discovered a shorter way to go to vertex C. Yep.
Check the C, not B, so we compare 6 with infinity.
Oh, right. Okay, never mind. Thank you. Because we're using V for the index and not U as the index. Thank you. Okay, so my mistake was using U in this place instead of V in this place, so you are correct. So we are checking the distance to vertex C and not vertex B. Vertex C currently has a known distance of infinity, and the alternate path has a cost of 6. 6 is definitely less than infinity, so we should update it. So I should not put it here. This one belongs to here. And because 6 is less than 43 or infinity, I'll change this one to 6. That's the first thing we do. The second thing we do is to change who is the previous vertex to this particular one. It used to be unknown or undefined, and now it is going to be which vertex? Vertex B, because U is variable U is storing vertex B. And then we change the priority. We are not going to change the priority, as I said. We are just going to re-evaluate every single time we remove something from Q. We just pick the one that has the least distance. Okay. All right. So that will end the conditional statement, which goes back to the beginning of the for loop. We have just evaluated the first neighbor coming out of B. Who is the other neighbor coming out of B?
Look it up.
All right. Well, you guys have a
Short memory span.
short-term memory.
E is 11.
Okay, so E is 11. Okay, very good. All right, so getting back to the algorithm, we're evaluating the alt for vertex E in this case. So we're going to put this value over here. What is the current known distance to vertex B, which is the origin?
5.
It's 5. What is the cost of that edge going from B to E?
11.
It's 11. 5 plus 11 is 16. So we're going to update that particular cell to 16.
Because it's less than 43.
Well, no. This is the alt. Okay, we are still doing this step here.
Okay.
Okay, but the next you are a little bit ahead of me because you are already evaluating whether the new distance is less than the current known distance to vertex E. And the answer is yes, okay? Because the current known distance to vertex E is infinity because we have not explored that yet. And yet now we have found a path to go from the origin to vertex E, and the cost is 16. Well, 16 is definitely less than infinity, so we'll go ahead and go into the conditional statement because the alt is less than the current known distance to vertex E. So the first thing we do is to update the current known distance to vertex E. It is now 16. The second thing is to update the previous. Previous is updated to the current variable U, which is vertex B, because that is all the way up here. And we are now also done with this step. Now that we are done with the conditional statement, we get out to the for loop. We have just considered both neighbors coming out of vertex B, so the for loop itself is also done. So we now have to go back to the while loop and ask, okay, do we have any other elements in Q? The answer is yep, we still have 3 things left in U, 2 things left in U at this point. So in terms of the spreadsheet, this is why it is kind of cool, because you can now scroll this column without affecting the first part. That makes it kind of easy to track things. This is the 3rd iteration of the while loop. In the 3rd iteration of the while loop, we are going to evaluate everything that is still in Q. Which vertices are still in Q at this point? When you look at the current column, okay, C, D, and E, they're all in Q. Which one has the least known distance? C has a known distance of 6, D has a known distance of 7, and E has a known distance of 16.
B still has the lowest.
Well, B has the lowest, but it's not in Q anymore.
C out of all of them.
Okay, C is in Q, okay, of all the elements that are currently in Q, C is the one that has the least known distance. So we're going to pick that one as our new variable U. So getting back to the trace here, so this time we pick vertex C as variable U, and as a part of that we also want to remove it so it is no longer in the queue after this step. So we are talking about this step here to extract that particular element out of queue. Are we still doing okay so far? Okay. All right. So now we go into the for loop and we want to ask the question, how many neighbors, who are the neighbors of C, vertex C? Well, let's go ahead and look it up. You guys can look it up too because the document is already shared. So there we go. So when we look at vertex C, it only has one neighbor, which is vertex D. Okay? So we go back to the trace here, and this neighbor V is now D, right? Okay, let me just double check. D, okay, C goes to D. Okay, so D is, the only neighbor. All right. What is the current known distance to vertex C? We just talked about it. That's how we picked it up. It's 6, right? What is the cost of the edge going from C to D? Was it 4? Okay, let's double check. C to D has a cost of 4. And what is 4 plus 6? It's 10, okay? So an alternate path has a cost of 10 to vertex D. Is 10 less than the current known distance to vertex D? It is not. In other words, what this is representing is we have just found another way to go to vertex D, but the cost of that particular path is not less than the current known shortest path to that vertex D. So should I update who is previous? The condition of the conditional statement is false. Should I go update anything? Nope, should not update anything. So now I go back to the beginning of the for loop, which is looking for another neighbor of vertex C. Vertex C only has one neighbor, so I'm done with the for loop. When I'm done with the for loop, I go exit the for loop, which goes back to the beginning of the while loop. And the beginning of the while loop says, well, as long as there is still something in Q, we have to keep going. Are there any other elements in Q at this point? Okay, we have D and E in Q at this point, so we have to go for another iteration. And in the spreadsheet, this is how we do it. We just move on to the next row or the next column, and then we ask the question. Out of the 2 elements that are left in Q, which one should I pick at this point? Which one has the least distance? D has the least distance. So for iteration 4 of the while loop, we're going to pick vertex D as a variable U, and then we evaluate its neighbors. So now we have to look up the neighbors. Vertex D has only one single neighbor, which is vertex E. Okay. So when we get to remember to get this one out of the queue first. So we put a 0 here to represent that vertex D is no longer in Q. Then we can go for the for loop. We only got one neighbor in this case, which is vertex E. And if I look it up, vertex E has a cost of 10. Just trying to find the right window right here. Okay, so V is now E because that's the only neighbor of vertex D. What is the current known distance to vertex E? It's 16 at this point. Okay, what is the current known distance to D?
7.
It's 7. And what is the cost of the edge going from vertex D to vertex E? 10. 7 plus 10 is
17.
is 17. Is 17 less than 16?
No.
So we don't have to update anything. And that concludes this particular for loop. Yep.
Wait, you just confused me there. Isn't the distance this to you 7?
This to
Yes.
is 7, but the length going from vertex D to vertex E is
10.
10.
Oh, that one, yeah.
So 7 plus 10 is 17. So in other words, we just found a new path to go to vertex E, but the cost is 17 units. But the current known shortest path coming from D has a cost of 16. So there's no need to update anything because I didn't find a better path to go there. Is that okay? So that means I'm done with the for loop because of the condition of the conditional statement is false. I do not get into the conditional statement, and there are no additional neighbors to consider. Is that okay? All right. So now that we are done with this one, we exit the for loop. We go back to the beginning of the while loop. The while loop is asking, is Q empty? Q is not empty yet. Okay, we have one thing left. Okay, so we're gonna duplicate this column to over here, and then we have iteration 5, and we just need to keep track of alt in this case.
So in iteration 5, there's only one thing left in Q. It doesn't really matter how everything is ordered. When you have one thing, there's only one way to order it, right? Because the permutation of 1 out of 1 is 1. See, I'm throwing in all of these things here, okay? Permutation. What? So since we only have one thing left, well, it is important to kind of remind you guys of all the concepts that you should know already at this point. So we remove it out of the queue, change this one to 0, and E becomes our U at this point. Now we have to find the neighbors of E. Okay, so we go back to this slide here. E has two neighbors. E has a neighbor of B with a cost of 2 and a neighbor of C with a cost of 3. In other words, we have a loop in this particular graph. But that's okay, because the Dijkstra's algorithm can take care of this without any problems. All right, so now that we take this out of the queue, oh, I forgot this one. The next thing we need to do is to go into the for loop here, and we have the two vertices to consider. One is B and one is C. So we look at B first, okay? And then we say, okay, what is the current, what is the cost of this new way of going to vertex B? Is through vertex E. Vertex E has a cost of 16 to begin with, plus 2 is 18. So alt is 18 for vertex B. And the next question is, did I find a shorter way to go back to vertex B? The answer is no. Okay, because this was the shortest path known at this point, and this is the alternate path, which is through a loop, and it is not any less than the previous one. I'm not going to execute the body of the conditional statement. Now we consider vertex C. Vertex C has a current known shortest path of 6 units of cost, and I'm now going to consider 16 plus 3, which is 19, right? And then we compare alt, which is 19, to the current distance, current known shortest distance to vertex C, which is only 6. 19 is less than 6 is false. We do not perform the body of this conditional statement. And then we go back to the beginning of the for loop. There are no additional members, or there are no additional neighbors of this particular vertex, which is E, and I'm done with the for loop. When I'm done with the for loop, I go back to the beginning and look at, do we have anything else left in Q?
No.
The answer is no, we got nothing left in Q, and so the algorithm is concluded at this point. Are we, yep, go ahead.
For this example, where were we trying to get to, and how would we show with the work that we've done which distance is the shortest?
Well, we already know the shortest distance to every single cell, to every single vertex.
From our origin, which we've assigned to as A.
Right, correct. So let's take a look at, I need to move this point. Oh, we need to change the hand. There we go, there we go. All right, so I'm going to maximize the spreadsheet itself. It should look like this, okay, to reflect how you get to the solution. But in the end, the actual shortest paths to any particular node is indicated by column C. Column C is the key to get everything, to get to the shortest, to find the shortest path to every single vertex. Okay. So let's go ahead and just draw this out this time. Okay. So we'll draw A, B, C, D, E as a graph. And we'll go ahead and update all of these edges here. A does not have a previous because it is the origin. Okay, there's no one before that. When you look at vertex B says, okay, go to vertex B from vertex A. That is the shortest path to it. I'm sorting all of these whiteboard markers, and the cost of this is what? Okay, so this one has a cost of 5 to vertex B. You look at vertex C. What is the quickest way to get to vertex C? Through vertex B, right? And the actual cost of the shortest path has a cost of 6 units. You look at vertex D. Vertex D says the shortest distance to vertex D, excuse me, to vertex D is 7, and through whom should I go there? A. And how about vertex E? Through which vertex? Yep. And it has a cost of 16. There you go. Now, what does that remind you? Okay, let's think about all the concepts that we have talked about so far. Okay, it's a graph for sure, right? But this is a subgraph of the original graph. The original graph has a lot more stuff in it, but this is a subgraph. And what are some of the special properties of this subgraph? Does it have any loops in it?
Yes.
No. Just looking at this subgraph, the one that is on the whiteboard right now, does not have any loops. Yep.
So it's like a binary tree.
It is a tree, okay? Not necessarily a binary tree because
Yeah, not binary.
in this case it is because you can look at there are no single vertex with 3 or more outgoing edges, so you can quote unquote call it a binary tree, but that's not a general rule. Okay, but it is a tree. In fact, this is not just a tree, it is a minimum spanning tree. In other words, this particular tree, of all the different ways to construct a tree out of the graph, this one has the minimum cost when you add up all the edges. Have we talked about minimum spanning trees just yet, or not? Don't think we have touched on that one yet. Okay, but this is important because it's called a minimum spanning tree, which is actually very useful in many applications. We'll talk about that, maybe later today. We have enough time today to start on that one. So your homework assignment is like this, except the graph that you're dealing with is a little bit more complicated, so it will take you just slightly more time. Yep.
So the total cost is all the distances that you have to travel. So 5, 6, and 7. So that's 20 or
Not.
18. So
No, the cost of a minimum spanning tree are the cost of all of the edges.
not including duplicate.
Do not include duplicates.
Okay.
Yep. Mhm. All right. So are there any questions about how to do your homework assignment? Does anyone want to check to make sure that you can, in fact, access that spreadsheet?
You can.
Yep, it's good? Okay. Can you save it? I know you can read it. Can you save it as your own?
Yes.
You can
Okay.
download it.
You can download it? Okay, great. There you go. So I think this is a relatively reasonable starting point of your homework assignment. Are there any questions about the homework assignment?
How many points is it worth?
A lot.
50?
Yeah.
Yeah.
Probably good.
Which is good for
Yeah.
if you have missed some homework assignments before. All right. If there are no questions about this, I'm going to go back to my slides here. So I do want to get to trees. I cannot remember how far we got in terms of trees.
We talked about RB and
Red black tree.
yeah.
Okay. All right. So we talked about red black tree versus AVL tree. I remember that part. And we talked about. Did we talk about why trees are so useful?
This is where we're at.
This is where we are at. Okay.
About like one paragraph up from that.
Oh, okay. All right. So trees are really useful because the traversal of a tree is easy. Okay. This particular algorithm here, which is depth first search, is a very generic algorithm. So let's take a look. Let's take a quick look at this particular algorithm. The algorithm takes 1, 2, 3, 4 parameters with only one real actual parameter. So vertex V is the only actual parameter. Pre, mid, and post are basically things to do. Okay, they're basically, if you will, pointer to functions. Okay, in C it's a pointer to functions. In C++, I think you can encapsulate it with a particular class with only one method in it. Okay, but it's basically something to do. When you first get into the algorithm, in one particular invocation, the first thing you do is you perform the pre-operation. When you perform the pre-operation, you are doing it to vertex v, which is the parameter to this particular subroutine. And then what you do is for each child c of v, okay, in the terms of a tree, a child is kind of like a neighbor, because especially in the case of a directed tree, a child is a neighbor of a tree. So this is basically saying for each neighbor c of v, do the following. The first thing you do is you perform the depth first search with that particular child. And then the second thing you do is if that particular child is not the last child, in other words, there are additional children for this particular node or for this particular vertex, you want to perform a mid operation, MID. But the mid operation is not done to C, it is done to V itself. Okay? And then when you're done with this one, okay, when you're done with the for loop, there is a post operation to perform to the node V itself. This is the most general way to traverse a tree. So if you want to draw a picture of how this is actually done, then it is, I'll just give you a sample here. So I'll give you a sample of A, B, C, D, E, and then we have F and G here. Okay, so this is the graph here. And if I want to express the ordering of all of these operations, let's take a look at how these things should be ordered. What is the first operation that I'm going to perform in terms of pre, mid, and post? This is the root. A is the root of the entire tree. So we're going to first perform pre-A first, right? The pre-operation of A, that's the first invocation. And then what do we do next? We do not do anything with V. We do not do anything with A anymore. We call DFS, depth first search, on B. What do we do in what do we do in that particular invocation when vertex B is parameter V? We do pre, okay? We always do pre. So we do pre on B. Does B have any children? No, it is a leaf node. It does not have any children. So therefore, there's no mid operation either. Is that okay? You only perform the mid operation when it has its own children. It does not. So we skip all the way to the post operation. We perform the post operation on B. And then where do we go next? This is the second invocation of DFS. We go back to the first invocation of DFS, right? So we now explore the other child of A, which is vertex C. So now we go pre-C. Does C have any children?
Yes.
C has two children. It has F and G. So now we call DFS recursively first to F, right? F is going to have the pre-operation done first. Does F have any children?
No.
F is a leaf node. It has no children, and therefore there won't be any mid operation performed to F. And then what do we do after that? Post F, right?
And then we go back in and we call it first.
And then we go back to the second invocation of DFS, and now we are saying we're to mid C, right? And then after that, what do? We go DFSG.
Pre-G.
So we have a pre-G,
And then post-G.
and then post-G because G has no children.
And then we do post.
And then we are done with this invocation. We go back to this one here. C has no additional children and post-C. And then where do we go?
D.
We go back to A, right? But when we go back to A, I think I missed one mid, which is okay. I missed one. This will make an excellent exam question. Where should that mid go? What am I missing so far?
It should go after
That would be great because I can do this with a program.
Well, you said if C is not the last child, do mid B, so I said.
No. I'm missing one mid here. A has one mid operation between B and C.
The mid needs to go between post B and pre-C.
Exactly. Post B and pre-C should have a mid A here. Okay? And now that I'm done with post C, between C and D, I should also have a mid here. Is that making any sense? So I have another mid A, and then I traverse to this node here. So I have a pre-D, post-D, and then back to A, do another mid-A here. A, pre-E, post-E. And I'm not done yet, okay, because I need another post for A here. There we go. So this is the sequence of all the pre, mid, and post operations. Now, why is this useful?
It shows you work on traversal and work ending on each.
Okay, so depending on what you're doing, sometimes you only need the pre-operation. Sometimes you only need the mid-operation. Sometimes you want to have the post-operation. Now, this is only for traversing. I'm not changing the tree in any particular way. I'm just traversing the tree. If I want to nuke a folder, if I want to remove a folder from a file system, where the rule is if a directory is not empty, you cannot remove it, okay? What will be corresponding to these operations?
Pre would be checking the folder to see if it has anything in it. If it does, you go to that first child, say, hey, does this have anything in it? And you keep going down the line until you find an empty file, and mid might be delete.
Well, mid has nothing to do.
Okay, so
mid actually has nothing to do. There's only one operation that needs to do something when you're deleting, you know.
That'd be the post.
If you think about A, B, C, D, E, F, G as files or directories, there's only one thing that you need to do if you want to nuke this folder. It is the post operation. The post operation is delete. Okay? Because you cannot delete A until all of the subdirectories or files are deleted. B is okay. B is just a file. Okay, you can just delete it. But C you cannot delete until F and G are deleted. So when you look at the ordering of the post operation, it guarantees that F and G are both deleted before C is deleted. And it also guarantees that B, C, D, E are deleted before A is deleted. Okay. Is that making any sense? Yep, go ahead.
So we're treating A like a folder, B, C, and D like subfolders, and F and G like files, because F and G have nothing contained. In this particular example.
Okay, A and C must be folders because they contain something.
Right.
The other ones, which are B, F, G, D, and E, can be either files or empty subdirectories. So they can be deleted without having to delete anything else.
Gotcha.
Okay. All right. Well, this is one reason why tree traversal is important. Are there any other reasons why tree traversal is important? Let's look at expressions. Okay, expressions that you typically use in a math class or in this class or in many other different classes. So we'll take a look at this one here: A plus B times C, the whole thing divided by, I don't know, D divided by E plus F. Okay. All right. Yep.
Sorry, this is kind of late, but what's pre, mid, and post again?
Pre is before, mid is during, and then post is after.
Oh, but what kind of, is it just like in terms of checking, in terms of...
Oh, they're just operations.
Oh.
In other words, they are simply representing operations that you might want to perform at this stage, and also at this stage.
Gotcha.
So they're basically just optional things that you can do during that point. At that point. So I'm just now we're evaluating what does it mean when you get to a particular place. What are you actually doing? Well, that depends on the application. What your tree is actually representing. This is representing what you're doing when you're deleting a tree. This, on the other hand, is the evaluation of expressions. Okay? Can someone tell me how to express this as a tree? What is the root of this entire tree? What is the last operation I need to perform? It's the over, right? It's the division. Okay. What are the two things? What am I dividing from what else? Okay, let's look at the numerator first.
Multiplication.
Multiply.
Addition.
Addition. A, B, and C over here. How about the denominator? There's another division. D is here, and then we have addition, E and F. All right? So this is a tree representation of an expression that you typically use. This is called an infix notation, okay? Which means the operator is between the two things that it operates on. Okay? So why do you think tree traversal might be important in this case too? How do I generate the prefix notation? We kind of talked about it last time. The prefix notation would make use of the pre-operation. So the pre-operation will spell out the operator itself with an open parenthesis, right? What about the mid operation? Specify the space or the comma in between the parameters, right? What about the post operation? Close parenthesis. So if you design EFS and perform the operation of pre, mid, and post the way we described it, and you traverse a tree like this, you end up with a prefix notation of this particular structure. I just need to reactivate the screen here. What about a postfix notation? How do I traverse this thing and come up with the postfix notation?
From the
Okay.
lowest.
What are we going to do with each of these things? Pre, mid, and post. There's nothing to do with pre. There's absolutely nothing to do with pre. Mid is kind of like a push operation, okay, the separator thing. And then the post is the one that specifies the operator. Okay, so let's just kind of take a look at this one. We only got
Just
a
do
minute and a half,
mid-post.
but I think that's enough time. So we do a depth first search, nothing to do with the pre, nothing to do with the pre, nothing to do with the pre. Get to this part here, okay? So we spell out, we push A, we push B, and then we go back to plus here, and spit out the operation, which is plus. We go back to the multiply, nothing to do for the mid, I'm not done yet. Then we go to the other branch, C, we do the post operation, emit the C, and then we go back to the asterisk here. This is the time to do the post, which spits out multiply. We go back to here, we're not done yet, it's not time for the post operation. We go down here, nothing to do yet. We go down here, and we will do the post operation because there's nothing after this. So we emit D. We go back to here, nothing to do yet, nothing to do, E, okay. Nothing to do yet, go back to F. When we go back to plus, now we perform the post operation, which is a plus. Then we go back to here, we do the post operation of divide, and we go back here, we do the post operation, which is divide.
So it's just mid and post constantly.
But you can see, but the importance is the representation. This is the representation of what we want to do. How you want to represent it, which is the infix notation, the prefix notation, and the postfix notation, are just different ways of defining the pre, mid, and post. So that is kind of why this is really important, because once you have something that is a tree, by changing what you do as you traverse the tree, the outcome is something that is different. All right, we are running out of time today. On Thursday, we'll have a practice exam, and then on next Thursday, we'll have the actual final.
Do we have class this Thursday then?
Yes, we do.
Next
This-
week, Wednesday is the last day of class. Thursday is
So we
Thursday.
have 2 lectures left. We have this Thursday and next Tuesday.
A week from Thursday.
A week from this Thursday. Yeah. 9 days from today.